So we are going to go ahead and pick up where we left off with this implicit differentiation stuff. So we've got one more example where we're just finding the derivative. And with this one, we've got a nested function that requires a product rule. So let's work our way through that one. So remember, just like all the ones before, what we're doing is we're taking the entire function, left-hand side, the right-hand side. We are taking the derivative with respect to x of the left. We are taking the derivative with respect of the right. So starting on the left-hand side, like I said, that's going to require a chain rule, and so our main function is tangent. So let's work on the tangent part. So the derivative of tangent is secant squared. Then we leave the nested function in place. That's an x squared times y. And then remember, what we're supposed to be doing is multiplying by the derivative of the nested function. Well, when we do that, that requires us to use a product rule. So let's see what that's going to turn out to be. So the first function, which is x squared, and then times the derivative of the second. So remember, every problem that we've been doing so far, whenever we need to take the derivative of y, keep in mind here, I know I covered it up with the d by dx, we are finding the derivative with respect to x. So when we want to find the derivative of y with respect to x, we literally write down the notation that means derivative of y with respect to x. And then plus, now we finish off the chain rule, the second, which is the y, and then times the derivative of the first. So the derivative of 2x the derivative of x squared, jumped ahead of myself there, the derivative of x squared with respect to x is a 2x. There's no like dx by dx required because that would just be 1. So that's the left-hand side. We've got our product rule inside of a chain rule here. So we took the derivative of tangent, which is secant squared, left the nested function in place, and then multiplied by the derivative of the nested function, which required a product rule. Equals, then we've got chain rule going on the right-hand side as well. The main function is a cubed function, so the 3 comes out front, power drops down to 2, and then we multiply by the derivative of the nested function, which is the derivative of x plus y. The derivative of x is 1, and then plus, again, the derivative of y with respect to x. We literally write derivative of y with respect to x. So now this one, it's going to be super, super fun to get the dy by dx by itself. Notice here that this secant term is supposed to be distributed to both of these terms, and this kind of polynomial term is supposed to be distributed to both of these terms. So we need to do that first before we start to isolate our dy by dx terms. So we have multiply right here. Let's put the x squared out front of the secant squared of x squared times y. I've got a dy by dx attached to that. And then I will distribute my secant term to this term right here. Again, I'm going to put anything algebraic before anything trig related. Okay, that's my left-hand side once I distribute that secant term. And then equals on the right, I have to distribute this 3 times x plus y squared term. So distribute it to the 1, and I just get 3 times x plus y squared. And then distribute it to the dy by dx. So then plus 3 times x plus y squared times dy by dx. All right, so next thing we need to do is remember anything that has a dy by dx, we're going to gather it up on the left-hand side. So this term right here and this term right here belong on the left-hand side. So let's start with that. So this term's already on the left-hand side. And then this other term that I underlined over here, it needs to be subtracted over to the left. So then minus 3 times the quantity x plus y squared dy by dx equals, here's the 3 times the quantity x plus y squared that already was on the right-hand side because it doesn't have a dy by dx, and then this term right here I'm going to subtract over. So then minus 2xy times secant squared of x squared times y. Alright, so last thing that's going to happen, and this has happened in all the problems so far, so hopefully we can kind of do this quickly. This dy by dx, remember I am going to take this term right here and I'm going to factor it out, so I'd be left with these two terms. So then to get the dy by dx by itself, I would divide both sides. So I am going to divide both sides with the leftovers here after I factor out the dy by dx. Okay, so this would be our dy by dx. And I know what you're thinking. And no, we can't cancel out the 3x plus y squareds. And no, we can't cancel out the secant squareds. All right, so that is your final beautiful answer for that one. Example 6, we've got a couple pieces here where we are going to take the second derivative implicitly, which is exactly as fun as you would imagine it would be based on the title. So let's start with the first one. So remember, this is just the Leibniz notation that means to take the second derivative. So we start with our original function here. Now notice it's not going to be like a y prime, y double prime, because the y is implicit. It's mixed in with everything else. So we just start just like we did with all the other ones, by taking the derivative with respect to x of both sides. So on the left-hand side, the derivative of 2x cubed with respect to x is a 6x squared, minus the derivative of 3y squared with respect to x is a 6y. I do the derivative part, but then remember, since I'm technically doing the chain rule, I multiply by dy by dx. And then that just equals 0 because 8 is a constant, and the derivative of a constant is always 0. So now I want to solve for dy by dx because that gives me my first derivative. So let's subtract 6x squared from both sides. And then divide both sides by the negative 6y. So what I get is dy by dx equals, I can reduce down these negative 6's, I get x squared over y. So that's the first derivative. Now what I'm going to do is I'm going to take the derivative of that. So let me just demonstrate in a different color here. Now I'm going to take the derivative of the left. I'm going to take the derivative of the right. While we're talking about notation, if you're wondering why this Leibniz notation, the Leibniz notation is set up the way it is, taking the derivative of dy, that's where the d squared y comes from, and then dx is where I get the dx squared. So just in case you're wondering, like I said, where that notation comes from, it's from taking the derivative with respect to x of dy by dx, and just kind of playing around with those variables. So when I take the derivative of the left-hand side, not really taking the derivative, but I end up with this notation, equals, and yes, you do get to do a quotient rule on the right-hand side. Thank you for asking. So let's do low, d high. So low is y, and then times d high, so the derivative of x squared, which is a 2x, minus high d low, that would be a dy by dx, derivative of y with respect to x, and then all of that over low. Okay, last thing, we are just about done. We cannot leave this in our expression. But the good thing is, we know what that is. It's right here. dy by dx is equivalent to x squared over y, so anytime that it pops up while I'm taking the second derivative, I just replace it with an x squared over y. So let's write this as 2xy minus x squared times the quantity x squared over y. All of that is over a y squared. You know me better than to think that I would just leave it like this, because you know I'm not going to. So over here, let's make sure we can get a common denominator. So we're going to multiply this by y over y, because this one will have a denominator of y, so I want to make sure this one will as well. So let's combine up. So I will get a 2xy squared, and then minus x squared times x squared gives me x to the fourth. Now I can put that all over a common denominator of y, but that's technically just my numerator so far. I can put all of that over a y squared. So last revision here, I've got the 2xy squared minus x squared, I'm sorry, x to the fourth, and this all ends up over a y cubed. Because really, rather than dividing by y squared, I'm going to multiply by 1 over y. So that is my final answer. That is the second derivative. I think we have one more second derivative problem. Yes, we do. So we're going to compute y double prime at a specific point. So let's start working on that. So here is our original function. Again, just like all the others. Take the derivative of both sides with respect to x. So the derivative of x cubed with respect to x is a 3x squared, plus the derivative of y cubed with respect to x. 3 comes out front, power drops down to a 2, and I multiply by dy by dx, because my nested function is a y, equals, now on the right-hand side, the derivative of 3x is just 3, because it's a linear function, which always has a constant derivative, plus the derivative of y with respect to x, so I write dy by dx, and then minus technically 0 because the derivative of 2 is just 0 because it's a constant. All right, so now, same thing as we've done with all the other problems. We want to get those dy by dx's all by themselves on one side of the equation. So let's start there. So I'm going to keep the 3y squared that's attached to the dy by dx. I'm going to keep that on the left-hand side. The 3x squared I will be moving over. I will subtract this term. It's just a dy by dx, which means it's technically attached to a 1. Keep that in mind. Equals the 3 that was already over here, and then minus the 3x squared that I subtract. So let me just show you really quickly. When I divide out, when I factor out a dy by dx, remember that there is technically a 1 in front of that dy by dx. Do not forget about that. So to get my dy by dx by itself, I divide both sides by the 3y squared minus 1. So I get 3 minus 3x squared, and then divided by these leftovers, the 3y squared minus 1. That's my first derivative. All right, so that's where I'm at so far. I'm going to do the exact same thing that I did on the front when I take the second derivative. Okay, so when I take the second derivative, d squared y by dx squared equals, and now I've got another beautiful quotient rule at hand here. So low, which is 3y squared minus 1, d high, so the derivative of that numerator, derivative of 3 is 0, and then minus a 6x, so a negative 6x, minus high, d low, the derivative of 3y squared, 6 times y times dy by dx, and then technically minus 0, because the derivative of 1 is just 0. All of that over 3y squared minus 1, the denominator, quantity squared. Okay. So this one is a little bit different because I am specifically looking for the derivative at the point 1, 1, which means every time I see an x, here, here, I can just plug in a 1. Every time I see a y, here, 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 I can just plug in a 1. Last thing, what do I do when I see this? Well, I want to know the first derivative at the point 1, 1. So let's go back up here. What is the first derivative at the point 1, 1? Well, I have 3 minus 3 times 1 squared over 3 times 1 squared minus 1. The numerator is 3 times 3. That's 0. The denominator is 3 minus 1. So that is 0 over 2, which of course is 0. So that means that the first derivative at the point 1, 1 is 0. So I'm just going to plug that in right here. So let's plug everything in that we've got. So 3 times 1 squared is 3, and then minus 1. Negative 6 times 1 is a negative 6, minus 3 minus 3, if I plug in the 1, and then 6 times 1 times 0, all of that over 3 minus 1 quantity squared. So all I did in that step was I replaced each x with the number 1, I replaced each y with the number 1, and that comes from this point up here, and then I replaced the derivative with 0, because at the point 1, 1, the first derivative came out to be 0. So this is 0, this is 0. Let's clean up everything else. So this is a 2. 2 times a negative 6 gives me a negative 12 in the numerator. And then 3 minus 1 is 2. 2 squared is 4. So the number that I'm looking here turns out to be a negative 3. All right. This first AP problem, I want to leave for us to do by ourselves because this is an entire AP problem all based around implicit differentiation. It's beautiful. And it's actually, I think, the first full AP problem that we're capable of doing. So I wouldn't want us to miss that joyous experience together as a class. But there are a couple little ones that we can do right here on the video. So a multiple choice option here. This is on the non-calculator section of the multiple choice test, number 19. Anything 1 through 28 is going to be non-calculator. So it gives us a function. It's not terrible. It's a little quotient rule required. They want to know for which points does f have the property that the tangent line has a slope of 1/2. Okay, so what we're looking for is that the tangent line has a slope of 1/2. So in other words, we're looking for specific points where y prime is equal to 1/2, or if we want to be more accurate to the way that we normally write this, we want dy by dx to be 1/2. All right, so let us worry about taking the derivative right here. Now this one really just has to do with derivatives. There's not really any implicit differentiation involved, so that's why I figured we're fine to do this together on the video. So f prime of x equals, I do low, d high, the derivative of x is just 1, and then minus high, d low, derivative is also 1. All of that over low, low. So when I clean this up a little bit, I have an x plus 2 minus x. The x's will cancel. All I have left is a 2. And then over the quantity x plus 2 squared. So I am interested in finding a place where this is equal to 1/2. So we can kind of do just a little like ratio setup. Like 1 over 2 is equal to 2 over 4. So that means that x plus 2 quantity squared must be equal to 4. Now keep in mind, you guys are probably looking at this and thinking like, oh yeah, 0. 0 plus 2 squared gives me 4, so it must be 0. However, keep in mind that squaring a number makes it positive regardless, so I could have a negative answer in here. How would I get a negative 2 to square it? Let's do the actual work. When I take a square root, I'm left with x plus 2 on the left. Keep in mind, like I said, that I'm left with positive or negative 2 on the right. So when I subtract 2, I could get 2 different answers. X equals 0, but x could also equal negative 4. All right, so that will leave us with the third option there, which has 0, 0, and then it also has the point negative 4, 2. Don't forget about that second answer. Very common mistake to just write the letter A. All right, last one here. We can do this together as well. This one basically hands you the first derivative, just with a slight tweak that you need to make. All you need to do is divide both sides by the x plus 2y. So that right there is our first derivative. Keep in mind with both of these problems that these are multiple choice problems. There's no work required. So whatever you think you can or can't do in your head, you're probably fine. Because like I said, the only thing that counts is the final answer. There's no work that they give you credit for. There's no work required, nothing like that. So for this one, this is going to be very similar to the ones we just did on the previous page, except we don't have to do the work to get the first derivative. We just have to do the work to get the second. So d squared y by dx squared, Leibniz notation for the second derivative, equals, I'm going to do a little quotient rule. So the first times the derivative of the second. So the derivative of 2x is 2, minus the derivative of y, which is dy by dx, minus, I'm sorry, I've been saying first and second. Low, d high, you know what I mean. Low, d high, and then minus high, d low, the derivative of the denominator. The derivative of x is 1, plus the derivative of 2y is 2 dy by dx, over x plus 2y quantity squared. So a lot of plugging in to do. They are looking for this value at a specific point. So what I'm going to do is I'll plug in the x. So the x is 3, 2y would be 0, 2 minus, and then I get stuck. What is dy by dx? Well, I need to plug it into my original function to see what the first derivative is at this point. So let's do that over on the side. So 2 times x, 2 times 3 is 6, and then minus 0 over x, which is 3, and then plus 2y, which is 0. So this turns out to be 2. So anytime that they're looking for the first derivative, they want a value of 2. So I plug in the 2 right here. Minus 2x is 6, minus 0, and then times 1 plus 2 times 2. All of that over. X is 3, plus 2y is 0, quantity squared. So let's clean this up. So 3 plus 0 is 3, but I'm multiplying it by 0, so the whole thing goes away. Minus 6 minus 0, which is 6, and then 1 plus 4. So this is 5 times 6, that's a 30. So I've got a negative 30. Don't forget about the negative right here. And then over, this ends up being 9. So negative 30 over 9 reduces down to a negative 10/3. If you had forgotten this little negative sign, we would have had a positive 30 over 9. You would have answered incorrectly. So negatives can make a huge, huge difference in the course of your problem. All right, that's it.